University Prep Physics. Here is our first example related to an inclined plane. And the most common example is always a sled on a hill. So you have a sleigh, it's got this mass, it's on a hill, it's inclined 25 degrees, that's supposed to be degrees. The hill is icy, and we want the sleigh to not slide down the hill. So the sled is held at rest by a rope, and the rope is parallel to the hill. So it's asking us to find normal force and tension, and we've already talked about tension in the previous video. So let's solve this question then. It's not very difficult. Just looking at a picture then. Here's my hill, here's my rope, here's my sled, and I'm just looking to find normal force. And I'm not going to get into the why the normal force is mg cos 25 because I've already explained that in the note, but that's all it is. So solving for normal is actually really easy. 124 newtons, there's nothing else to do. Mg, mass of 14, times 9.8 times cos of the angle. And I'm going to say that number makes sense because if there was no angle and it was just resting on a surface, it would be about 140 because it'd be about 10 times 9.8. Or sorry, 14 times 9.8. And then I want to find the magnitude of the tension in the rope. Well, this is a system of static equilibrium. This thing isn't moving at all. That means that in this direction, which is my positive, is my x direction, tension is equal and opposite to mg sine 25. So, then tension is just 14 times 9.8 times sine 25. I think the number's around the same, it's around the same magnitude, but order of magnitude, so it probably makes sense. And that's really that example all done. Second example is a little more difficult. Here we're looking at a sleigh. We got an 18-degree angle hill, and we know the height of our hill, but we don't know the length of the hill. And we want to find the speed of the sleigh when it gets to the bottom. So it's starting at a rest, and it's released. It's not pushed. Let's assume that it's not pushed, and it's released. So few things. One is there's no mass given, so I guess we're going to have to assume it's going to cancel. If I don't give you mass, that's usually why, and usually not my mistake. And then it is a kinematics formula. We're looking at, velocity 1, velocity 2, so we're going to have to find acceleration so we can figure this out. And acceleration, of course, we can because we know we can figure out the force pulling it down the hill. So let's begin with that. So we can't say net force is 0, of course, because it's going to accelerate down the hill. We know the speed changes, so it's not net force of 0. So in the x direction, which, by the way, again, x direction is down the incline, my net force is my forward forces minus my backward forces. And if I look at the picture, I think it must tell us that we're assuming no friction. We're going to assume no friction. So the only force in question as far as the direction of motion is the mg sine 18. So that's the net force. Then we're going, okay, well, we can't solve for that because we don't know mass. But here's the thing. We also know that in the x direction, the acceleration in the x direction times its mass, Newton's second law, is equal to the net force. So then you can say mg sine 18 equals max, where ax is the acceleration in the direction down the hill. M's cancel, right? Just cancel out my m's here. They cancel. And g sine 18, oops, I should have done it here. G sine 18 is equal to my acceleration in the x direction. And this is, if there's no friction, the acceleration is always g sine theta, okay? So going back to the kinematics problem, of course I could solve for that now, 9.8 times sine 18, but I'm just going to leave it like this, because again, the less rounding you have to do in the solving of a problem, the better accuracy you'll get. So I have to pick a formula, the one that works. It's nice, I don't have to do x and y. I've already dealt with all that. V2 squared equals V1 squared plus 2AD. Well, V1 is 0, and I don't know D. This is the problem. So I come back to my incline. I know the height is 25, and I know the angle. So I can say, well, 25 over the hypotenuse, opposite over hypotenuse, equals sine 18. Cross multiply and divide to find my distance down the hill, 81 meters almost. So that's where this comes from. Okay, so this 80.9 meters gets used in my formula because that's how many meters I accelerate for. So starting at rest, when I put it under this here, since this is 0, I just cancel it. So V2 is the square root of 2AD and 22 meters per second, which is fast. Let's see, so that's what, times 4, like it's about almost 80 kilometers per hour, which is a little bit of Christmas vacation speeds, but it is what it is. I'm going to still a check mark because it's not unreasonable, it's just unsafe. Okay, so, but we also know that there's always a little bit of friction, and that's really what the next part of this problem looks like. In the third, part 3, it just says, okay, same question, everything's the same as we did before, except for let's just assume there's coefficient of friction. There is some friction, and it's light because it is a sleigh, a well-greased sleigh, and but it's 0.1. So now when I look at my free body diagram, I still have mg sine 18 pulling it down the hill, but I got fk holding it back. It's still going to accelerate most likely, so I purposely drew this vector to be a little bit bigger than that vector. So to find out the force of friction, well, it's normal times mu k. Normal we know is mg cos theta, mg cos 18 in this case, times mu k. And we can start to do our solving. So we're just dealing with one direction. We're not worrying about x's and y's or anything like that. This is our x direction down the incline. So the net force in that direction is the force pulling it down, mg sine 18 minus fk, right? I can't say these two are equal to each other. There's got to be an acceleration. So then I have to substitute all this stuff in. Mg sine 18 minus mg cos 18 uk. And at this point, if this was a test, you'd be very concerned about the lack of an m, but it's going to cancel. And please keep that in mind. These things cancel because besides equaling, all this, net force is also ma. Okay? So when I put, this is the next step. So from here, I substitute. I say, well, ma must equal this mouthful. Now my m's cancel, right? Because they show up in every single term. And it's important to know that if there was no m for some reason in this term, I wouldn't be able to cancel m's. They have to show up not just on every side of the equation, both sides, but on every single term. Anyways, this leads me to a equals all that, which is plug in g, right, and put it in your calculator, and you'd find the acceleration is 2.1. So a little bit less than the 3.0 in the last one. So now we can go ahead and use this equation again, where instead of 3.03, we use 2.1. Still the same length of the hill, that doesn't change. And now the speed's 18 meters per second. That was compared to 22. So thinking in terms of kilometers per hour, it's still really fast, like 70 kilometers an hour or something like that. But it's in this line. It's less than the last question. If I use my last question as my reference, it's less than before, which it should be because there's friction, right? But not a whole lot less because it's a little of friction, only 0.1 coefficient. Anyways, those are a few examples using inclined planes. I hope that helps you with your assignment questions and your tests and just your overall understanding. That's it.